Good afternoon. Where were we? We had just finished transition metals. The transition metals and transition metal complexes homework is due 1 week from today at 12:30. Next week's lab is electrochemistry, and that will definitely be happening. Oh yes, we're about to do nuclear chemistry. There's my focus. And we'll have 1.5 to 2 lectures on this. We'll have 1.5 to 2 lectures on organic chemistry, and then we'll be done for the semester. Now, and what I will say is, in my humble opinion, your mileage may vary, the electrochemistry was the last fairly hard thing to comprehend. Transition metal complexes, once you practice it, I would suggest it will be slightly more straightforward. Nuclear chemistry, a little more so. And while organic chemistry itself is a very challenging subject, our 1 or 2 lectures on it will hopefully be pretty straightforward. You all know where you want to be. You want to be ready for the 3rd exam. That means understanding voltaic cells, electrolytic cells, the Nernst equation. And to help you do that, we've had a homework and 2 discussions. And if you feel like you need more practice, of course, there are textbook problems. And I'm happy to point out some of those. And it is my goal that you will never run out of practice problems should you want them. And I will help to make that happen. And what it may look like at this point is, if you have the textbook, I might point you to it. If you don't, I might photocopy the textbook and pick some problems for you to solve. Anyway, but yeah. Okay, so where were we? We were going to talk about nuclear chemistry. Some of our presidents might call it nuclear chemistry, but we're going to call it nuclear chemistry. And anybody know any of the presidents that called it nuclear? I don't think Ronald Reagan did, but George W. Bush. Anyone know the Democrat who did that?
Was it Clinton?
Down home boy, Bill Clinton. Yep. So no party affiliation necessary, but if you wanted.
I grew up saying it too, because that's what I was taught.
Yeah, that's all. So where we're going to start is we're going to start with nuclear symbols. I've got an example here, carbon-12. Carbon-12 is how we're going to pronounce it as we refer to it, but the nuclear symbol is going to be C for carbon, and C is the chemical symbol from the periodic table, and let's see, so there's the whole nuclear symbol. The 6 down here is, of course, the number of protons. And every carbon atom in the universe has 6 protons. That's what defines it. Well, let's note that. So number of protons, also called the atomic number. And there's a letter designation to it that I believe it's actually Z, but we won't use that. Though if you do remember Z from the equation last semester, energy for the hydrogen atom in terms of n squared. Anyway, there was a Z in that. I would just refer to it as number of protons or atomic number. Sometimes we'll abbreviate number of protons, just number of P as well, because we're going to be asking questions about protons. The number up top, does anybody know what this number is?
Number 12.
Thank you. The number is 12. The number is the mass number. And the mass number is the number of protons plus the number of neutrons, where n is going to be number of neutrons. So mass number, number of protons plus number of neutrons. And from Chem 400, protons and neutrons both in the nucleus, hence the nuclear symbol, and in that nucleus are 99.97% of the mass of the atom, hence that's why it's last. All right, so first question for carbon-12, how many neutrons are there? There are 6. Now, isotopes, again, review from Chem 400, but worth talking about. So we're going to talk about 3 isotopes of carbon. They have carbon-12, 13, and 14. And there are other isotopes, but these are the principal ones. And since the protons are always the same, the only thing you have to add here is the mass number. We have mass number 12, 13, and 14. I will write the nuclear symbols for each of these down here. So the only thing different about isotopes is the number of neutrons. They're all carbon. I'm now going to tell you that carbon-12 and carbon-13 are stable isotopes. And stable is going to mean non-radioactive. And stable throughout Chemistry 400 and 401 has meant low energy, and that definition still applies. They are stable because they are low energy. The radioactive ones will have a specific higher energy that means that they will be radioactive. Carbon-14 is radioactive. And for us, what radioactivity, one definition of it is that the nucleus spontaneously breaks into 2 or more pieces. Nucleus spontaneously breaks into 2 or more pieces. We'll talk more about that, but that's generally what it means for us, a working definition. So there are ways in which you can have an idea when something is stable or when something is radioactive. And there's a little section about that in your textbook, but we're not going to be concerned with that. So I will not ask you which is stable and which is not stable. But we'll talk about other things. Now, a little bit about nuclear reactions. Before I go on, we will be talking mostly, if not entirely, about the nuclei. And so we won't necessarily be talking about the electrons this chapter. Sometimes we will, but focus on the nucleus. And if we need the electrons, we'll talk about them a little bit. So this chapter is different than everything else, which has been focused on the electrons. All right. So nuclear reactions, reactions that change the nucleus. 5 main types of radiation that can be produced by nuclear reactions. As an example, carbon-14 spontaneously, radioactively decays and emits a beta particle. Here is the nuclear symbol of a beta particle. It has a 0 up high for its mass number. It has a -1 for its atomic number or number of protons. That's interesting. And as an example of a nuclear reaction involving a beta particle, carbon-14 14 spontaneously radioactively decays, just like it says, into a beta particle. Plus something else. And our rules for nuclear reactions will be the following. Elements will now change for nuclear reactions, that's fine, but the mass numbers have to balance, and the atomic numbers, or number of protons, have to balance as well. So I guess right here I'm going to write rules for nuclear reactions. First one is that the mass number must balance. We'll call that rule number 1. Rule number 2, atomic numbers, I'm just going to, so number of protons must balance. So the number at the top here is going to be 14. That's what I mean by balance. 14 on the left equals 14 on the right. Number of protons must balance. 6 on one side and a minus 1 here. What does this number of protons have to do? It has to be 7. And if it's 7, what element is it? It has to be nitrogen. Because as weird as the this number is, and we'll talk about it in a second, if it's got 7 protons, it is nitrogen. That is the definition of nitrogen. So that's what I mean by these 2 rules. And any questions, not about the -1, we'll talk about that in a second, but about how to balance things. Now let's talk about the -1. Interesting. -1 protons. Well, let's see. All right. What is a beta particle? A beta particle is an electron that is created in the nucleus. And here I'm using my symbol for electron that I've always used. An electron that is created in the nucleus and immediately ejected electrons, not typically welcome in the nucleus. I guess that's a parenthetical. In the nucleus, and immediately ejected. As a neutron in the nucleus splits into a proton and an electron. As a neutron in the nucleus as a neutron in the nucleus splits into a proton plus an electron. And as we said, I'm going to write the process by which this happens down here. We haven't talked about the nuclear symbol for a neutron. A neutron has 0 protons, because it is a neutron. And protons plus neutrons, it has 1 neutron, 0 protons. That is the nuclear symbol for a neutron. I think this arrow was a poor choice because it's not a reaction. I'm going to do my reaction here. So I'm going to erase that. Sorry. How about a colon? Nothing up my sleeve. That's the nuclear symbol for a proton. 1 proton, no neutrons, mass number 1. according to our rules, mass numbers must balance, proton numbers must balance. If I do that, I have 1 equals 1 plus 0. Proton numbers, 0 equals 1 plus minus 1. And at least we've got the mass number and the proton number to match. And it will turn out that even though I'm covering this first, it was the second type of particle, so instead of alpha it was called beta. It is a beta particle. So from the nucleus's perspective, an electron is a beta particle. So, and that's how we think of it. Any questions about that? That's what it means by -1. This -1 helps to balance the process. And this is the electron created in the nucleus from the nucleus's perspective. So I'm just going to write from nucleus's perspective. Although I'm pretty sure if this were an English class, I should say from the nucleus perspective. There's no plural S's. Good. Chew on that for a minute. As we then move on to talk about the properties of a beta particle. And it turns out that the properties of a beta particle are the properties of an electron. And if you remember back to where we talked about electrons, and we actually calculated something called the de Broglie wavelength of an electron, we were typically using speeds of about 90% of the speed of light. Well, actually, I think we were using a little less, but for these nuclear electrons, they are about 90%. Moderate penetrating power can be stopped by heavy clothing or 2 millimeters of water, and moderate damage potential. And so these are things to keep in mind. We're going to talk about beta particles first, then alpha, and then gamma radiation. And what we will see is when I say moderate damage potential, you will see that alpha particles cause more, and gamma rays cause less. So it's somewhere. As an example, iodine-131 decays by beta emission and is used to treat hyperthyroidism. We're going to write the nuclear reaction for this. Looks like this is the process. We know that the mass number is 131. We know that the number of protons is 53. And we've been told that it will decay by beta emission. And this is a question you can expect on your third exam. Given this word, the sentence, write the nuclear reaction. And balancing. We end up with element number 54, that's xenon, and xenon-131. Questions about this? Okay, so for beta particles, sometimes you'll see the symbol that I've used now, which is with a -1 and a 0. Sometimes you'll see just the lowercase Greek letter beta, basically B with a tail on it. And sometimes you will see us thinking about it as an electron. So sometimes we'll see it. That's beta particles for now. Now we'll backtrack in the Greek alphabet and go to alpha particles. And we'll start with the definition of an alpha particle. An alpha particle is a helium nucleus. If it's a helium nucleus, how many protons does it have? 2. It's a specific helium nucleus with a mass number of 4, which is the most stable. And this is a lowercase Greek letter alpha. And so this is the symbol we will typically use for an alpha particle. And again, it's referring specifically to a nucleus. That means if we were to think of its charge, it would have lost its 2 electrons, and so another symbol would have that charge on it. Again, it won't usually, but you might see it. And a final symbol. Sometimes we write helium, or sometimes we write helium 2+. Guess if we're being complete. So those are the various forms of it. And again, a lot of what we're going to be doing here is writing nuclear reactions. Uranium-238 decays by alpha emission. We know that uranium has an atomic number or number of protons of 92. Notice anything weird about element number 92? That's where the filled-in letters stop. It is the last element for which there are stable isotopes. After that, neptunium, plutonium, etc., all of them are outline letters because they're all of the isotopes are radioactive. And the number in parentheses is the most stable isotope of them. Though none of them are stable, all of them are radioactive. And some of the ones, including uranium-238, are radioactive. Although, what does it mean to be radioactive? It means your nucleus spontaneously decays. Maybe a better way of saying it is that uranium is the last element you can find in nature. Because the isotopes of uranium are radioactive, but their half-lives, meaning the time in which it takes for half of it to go away, are 2 to 4 billion years. So you still can find some uranium out in nature as it is. Anybody been to Moab, Utah area? So if you go down to Moab, Utah, they have since closed it, but they have a uranium mine, or they used to have a uranium mine there, because you could pull it out of the ground. All right, well, here we go. Decays by alpha emission. That means one of the products is going, well, let's say this. The uranium nucleus radioactively decays into 2 or more pieces. One of them is an alpha particle. The other is whatever else balances the reaction. And in this case, we've got 90 protons, 234 as the mass number. And that adds up to, let's see, element 90, thorium. And just to be clear, you do not have to know the names of the elements, you just have to be able to write their chemical symbols on your exam. Any questions about that? All right, then let's talk about properties of alpha particles. Alpha particles common in heavy radioisotopes, those that have too large of a nucleus to be stable, travel at considerably slower speeds, but still 10% of the speed of the light, which is much faster than I typically move down the highway. Low penetrating power can be stopped by a piece of paper or 0.03 millimeters of water, and a high damage potential. Now we can talk a little bit about damage potential so far, but basically, the more massive you are, which just means you have more mass. More massive equals more damaging. I've never played professional football or even amateur football before, I should say American football even. But I would much rather be hit with a small person than a large person because of the damage potential. On the other hand, as less massive will be more penetrating. And so this is the most massive because it has, or sorry, the most damaging because it has the most massive of the particles that we will see. It is the least penetrating. And you can imagine that as the bigger you are, the harder it is to fit between things like atoms as you go through materials. I think that's all I want to say about that. But you will get questions about the penetrating ability versus the damage ability. Third type of radiation, gamma ray emission. And here's where I'll mention the fact that the first two were particles, alpha particle, beta particle. This is a gamma ray. What is a gamma ray? It is energy in the form of electromagnetic radiation. Ken?
Sorry, so the damaging and penetrating, so we should assume that penetrating is not damaging, or is it the same thing?
So the way so if we take an alpha particle, and we'll assume it's that big, and we take a beta particle and it's much smaller, you can think of, well, all right, if an alpha particle hits you, it's going to be stopped immediately because it's going to hit your skin and damage your skin. Whereas a beta particle has less mass and there is easier for it to penetrate through some of your skin before it damages you. And it will do less damage. So, I mean, think of a giant wrecking ball versus a smaller one. Right? The big one will do more damage and it will be harder for it to miss things. All right. So, what is a gamma ray? Energy in the form of electromagnetic radiation. And since it is energy, we will have wavelengths of it, but we will refer to it as a gamma particle, or sorry, gamma ray. And gamma is basically an alpha turned on its head. And since it is electromagnetic radiation, it has no protons and no neutrons, therefore no mass. And oftentimes, nuclear reactions will create gamma radiation, but we don't particularly care because it doesn't help us balance. You should always assume that gamma radiation is also made as well. Okay? And we're just not necessarily. And so, we just did this for uranium-238 2 slides ago. Decays by alpha emission and gives off a gamma rays 2. So here's our alpha particle. Here's our gamma ray. And I apologize, sometimes I call them gamma particles, but they are rays. They are just wavelengths of light, of electromagnetic radiation. I've got myself so far. We left this off before because it didn't help us balance anything. We'll include it now. Other product of this nuclear reaction, still thorium-234. And that's a 90. And the term for this nucleus that is also created is typically the daughter nucleus. Which I am not making up just because I have it. Properties of a gamma ray almost always accompanies alpha and beta emission, but often not shown. I mentioned that. High penetrating power can be stopped by 10 centimeters of H2O and low damage potential. And of course, since it's electromagnetic radiation, it does travel at speed of light, as does all electromagnetic radiation. I mean, gamma rays are basically similar to X-rays, except that gamma rays are specifically from nuclear reactions. And they can have different wavelengths, but they're pretty similar. Question?
Is there any way, if I had some uranium in an enclosed container and the alpha particles couldn't get out of it, is there any way that it could recombine with the thorium to make uranium, or is that just not possible with the volume sequence class?
So your question is, you have some uranium in a box, and it's making alpha particles and thorium-234. Can these two combine to make the uranium-238? The short answer is no. The longer answer is, and we'll get to this, is that all of this process, remember, is spontaneous, and spontaneous still means basically going from a higher energy state to a lower energy state, and this will be exothermic. Energy is being given off to the surroundings. That's the whole idea behind nuclear power. And so to put these two back together, you'd have to put their energy back in. Does that make sense? Yeah. So, but no, I mean, it's an interesting idea because you get some radioactive stuff in there and it does get complicated. Because if it's in your box, then the energy is presumably in there as well. But typically, no.
So, radiation occurs because the nucleus becomes unstable.
So right, so this nucleus has too many, let's say the wrong ratio of protons to neutrons. It is, let's see, it's losing 2 protons and 2 neutrons. It's getting closer to 1 to 1. Anyway, but yes, so it is unstable and it is spontaneously decaying.
So for element 43 up there, how come if everything's under a typical red P2? So how come it's a small?
Great question. So questions about technetium, element 43. It is ghosted out or outlined. All of its isotopes are radioactive. The short answer for this question, Travis, is I don't know. Let's see. I know that technetium is used for some as a radioisotope for some treatments, but I'm not exactly sure why. People do make it and then use it. But, no, it's a good question, so I don't know the answer. All right. So, no mass. Most penetrating, least destructive. That's 3. We said there were 5 types of radioactive emissions. 4th one is positron emission. We'll start with what is a positron. Again, that's a rhetorical question. It is a positive electron. What I mean by that is it has the same mass as an electron. But it has positive charge. And we'll start there, although we have more to say about it. Its nuclear symbol is beta with a +1 and a 0. And we'll talk more about this down here. But let's show you an example first. Phosphorus 30 decays by positron emission. P is for phosphorus, 30 is the mass number. Check the periodic table. 15 protons. I know, it says +1 in the proton spot, but it is an electron. But it helps us, and from the nucleus perspective, we will talk about what this means. Looks like that's silicon 30, as our daughter nucleus. Now, properties. So, as far as penetrating power and damageability, it has the same mass, so it has the same penetration and damage. Now, what does this mean? A positron is created in the nucleus. When a proton my notes say when a proton in the nucleus, but that seems a little redundant, doesn't it? When a proton spontaneously breaks into a neutron and a beta proton. So a proton is created in the nucleus. I already wrote. Oh, yeah. A positron is created in the nucleus. When a proton breaks into a neutron and a positron. If you'll recall, there's our proton. There's our neutron balancing it out. And I guess I don't have to write +1, but I like to. +1, and that is our positron. And without getting too physicsy on you, a positron is antimatter to an electron. What does that mean? Well, as far as this class goes, if you take a positron and an electron and collide them into each other, positron, beta particle, or electron. I don't know, I'm like, should I call it an electron? I'm going to call it an electron. It's a beta particle. It's an electron. They're two words for the same thing. If we allow these two to collide, what is the one product that we make? What is its mass number? 0. What is its proton number? 0. If it's 0 and over 0, what is it? It is gamma. Thank you. And so, really cool. I'm sure there are a million questions you could ask me about this that I cannot answer. But I think it's really cool. But you're basically taking a positron and an electron and the mass that is involved with those two particles and turning them into energy in the form of light. And where we're going, and we haven't really talked too much about how energy plays into this yet, although clearly it's complicated because we've got neutrons turning into protons and electrons, splitting into those two parts. Now we've got protons splitting into a neutron in another part that contains mass. So for now, it's complicated. But it's not that complicated at all. We just haven't finished the story. So why are we doing all this? Well, nuclear processes are there's a number and an increasing number of them that are involved with certainly healthcare and perhaps nuclear energy in the United States is currently decreasing as a source of power, but countries like France that do not have the geopolitical clout that the United States does, France gets 80% of its energy from nuclear power. So it is, and I would guess, and does anybody remember President Obama, our last president? It's been a while, you know. He didn't advertise it a lot, but he was pretty pro-nuclear power, no greenhouse gases. Other issues for sure, but no greenhouse gases. And the United States contains plenty of uranium in those Midwestern to mountain states, like Utah. Anyway, so sidebar, positron emission tomography, or PET. PET scanning is a nuclear medicine that basically you have an isotope that produces a positron. That positron then collides with the nearest electron, generates gamma rays, which then come out of the body because of their big penetrating ability, and you can use it to image different parts of the body. And of course, the complicated part is how do you put that tracer, that positron emitting radionuclide, how do you control its chemistry so it goes to tumors, or it goes to a thyroid, or it goes to your heart or your brain, so you can image it. Anyway, that's why we're at least getting this far into it. And one of the big things about it, these three-dimensional images, you can now create using complicated computer programs. Anyway, again, that's about what I wanted to say so far for that. Oop, there's more. Oh yeah, I listed some of the isotopes. And then we'll keep going. Fifth type of radioactive decay is going to be electron capture. It is the reverse of beta decay. And what I mean by that is an electron not in the nucleus gets sucked into the nucleus and reacts with a proton. to make a neutron. And for example, sulfur 34 captures a beta particle. And it's called electron capture. We know that a beta particle, from what we've said today, is an electron, so this is electron capture. We add them up, we check our periodic table, it turns out this is phosphorus. Now, and there are reasons that many of these reactions occur, meaning why does something occur by alpha decay versus beta decay? Not the subject of what we're doing today. Happy to talk about that outside of class, though, and there is a section in your textbook about it, but we're not. Question? For two, what's your question, Kate?
Because I look at it as like, would you tell us if there was electron capture to know instead of that way? Like,
Oh,
I would
yeah.
have done like 17 plus. But would you tell us that there's?
If this was a question on your exam, it would say sulfur 34
Oh, capture.
reacts via electron capture to, and so write the nuclear reaction. So if key phrase here is electron capture.
I didn't see it.
Now, so I'll have to check your conversion equation sheets because they're new to me. But as far as I know, you do have to know how to write an alpha, beta, all 5 of these particles. I don't think we give those to you. If we do, consider it a gift from somebody else, not me. So other than that, though, and you can expect to have, is it on there? Didn't want to have to take it. So, and there will be some of these nuclear reactions on your third exam, right? Because this is still material that's on your third exam. Third exam is electrochemistry, transition metal complexes, and nuclear chemistry. Only organic chemistry, the last lecture or two, we'll save for the final. So you should expect to be writing some of these reactions, and so then knowing your different particles in types of reactions. Questions? Other questions? That's all 5 of them. I thought we'd run through all 5 of them before we really start talking about energy and some of the other things that are going on. So we'll just check in. We'll talk about the differences between chemical reactions and nuclear reactions. Chemical reactions have the law of conservation of mass. And way back in the beginning, in Chem 300, and I might have mentioned this in Chem 400, it says, truly the law of conservation of mass in a non-nuclear reaction, mass is conserved. Of course, now we're doing nuclear reactions, but in a non-nuclear reaction, energy is conserved. For nuclear reactions, the sum of mass plus energy is conserved. Mass can be converted into energy and vice versa. It's kind of a famous equation, the relationship between mass and energy. E equals what? mc squared. And we're not going to do this yet, but energy is going to be in joules, mass is going to be in kilograms, and c is the speed of light. energy in joules, mass in kilograms, C equals speed of light, and that is squared. Travis?
So when a positron, electron, but if an electron has the mass of 1.6 times 10 and I'm assuming a positron would also have the same mass, what would the mass of a gamma particle be? Is it just electromagnetic radiation in addition to particle dispersion? So if mass is concerned, what is it?
Great question. So your question is positron plus beta particle or electron, they come together, they create, the term is they annihilate each other. Yes, meaning there is no mass left. Because in that process, all mass has been converted to energy. And so you're probably giving off a lot of different types and a lot of energy in the form of radiation. And I'm not sure, some of that is definitely going to be converted into heat somehow. So you know the masses, and all of it's converted into energy. There is no mass left. That is part of the nuclear reaction. And that is matter versus antimatter. Although, what I was careful to say is, I know that much. I don't know. It's very interesting to me, but I haven't done any research. Yeah, hopefully that answers your question. There's no mass left. Chemical reactions, kinetics can be 0th, 1st, 2nd order. There can be other orders as well, but if you remember way back to the beginning of the semester, those were the 3 that we did principally. And we had graphs for nuclear reactions, the rate of radioactive decay, always follows a 1st order rate. And again, we're going to talk more about that, but I just wanted to tell these are the 2 principal differences between nuclear reactions and chemical reactions. It's all 1st order kinetics now. Sometimes the product of radioactive decay is still unstable. In this case, additional decay steps will follow until a stable nucleus is formed. A well-documented decay series is that of uranium-238. It decays by alpha, then the daughter, thorium-234, decays by beta, and then it just keeps going. This is a little picture of what happens. You start with uranium, you do a whole bunch of nuclear decays, you end up with an isotope of uranium. And so the only reason to tell you about this is that you can have more than one radioactive decay. It doesn't. Okay. And eventually, yeah, you get down to here and it's stable. That's all I wanted to say about that. Now let's move on to kinetics. Like I said, for radioactive decay, it's always 1st order kinetics. There are 2 forms of the equation. This version here and here, those are the 2 versions. I mean, it's the same equation. But if you remember back to kinetics before, we always had concentrations here. And it was like concentration sometime T over concentration initially. N in this case is amount of radioactive material. But you can also put the rates here. These are rates of rate of radioactive decay. And that's actually what we typically measure. We don't typically know how much radioactive material we have if something's radioactive, it's giving off alpha, beta, or some type of particle, and we use a Geiger counter to collect how much radiation is going off. We get the rate of decay. And do you remember the first order rate law? Rate equals well, way back at the beginning, and this is part of why I like this unit, it sort of ties some different things together for us here and lets us revisit it. Well, first order rate law way back was rate equals K times concentration of A to the first power, right? That's what it was, and I'm not going to write that in, but I'm going to write N, where N is the amount of radioactive material. And what that means is that the amount of radioactive material is proportional to the rate of radioactive decay. That's why we can use either of these. This equation says the amount of radioactive material is proportional to the rate of radioactive decay. And so, when I have this version with rates in it, these rates will be, so it's like we're replacing the amount of material, which is pretty cool. Any questions about that? And then the final thing I'll say, and I've said it, I just said it, but I'll say it again. We need this because this is what we typically measure. And when we do the nuclear reactions lab, we will have what are essentially Geiger counters, and they will be measuring rates, and we will compare rates over time to get the rate constant and the half-life, which is, by the way, an awesome lab. And I hope we get to do it. We are scheduled to. At this point, that's all I can say. All right, well, the half-life equation is the same, okay? So it's the same one as you had before. The half-life is 0.693 over K. I don't need to give it to you again because it's the same as it was before, although I bet it's on there again. And we derived this back in the Kinetics chapter. The derivation for this just says that the half-life is the time T half when you have half of the original amount left. And so you could actually derive this for yourself. We've already derived it for you, but that's where it goes. Good. And so we're going to pretend that we can know, oh, there was nothing written on there, so there's nothing raised. Good. So calculating mass left, so radioisotope iodine-131, again, used to treat hyperthyroidism, as we mentioned before, has a half-life of 8 days, 8.0 days. If a patient is given a dose of 18.2 milligrams of this isotope, what mass remains after 28 days? If you're getting this weird sense of deja vu, it's because you could have been asked this in the Kinetics chapter with different numbers. Our initial amount of material, n sub 0, n at time equals 0, is 8.2 micrograms. We're interested in the amount of radioactive material left. We know that the half-life is 8.0 days. And even though we've been given an equation in terms of the half-life, we can rearrange this to solve for the rate constant K. By cross-multiplying or what have you. And you get 0.0866 days to the minus 1. Now we're going to be solving for n sub t. If you remember, there's another version of this that instead of natural logarithms had an exponential function. And it looks like this. So this is the same equation rearranged. This too, we have to. And then it's just a matter of plug and chug until we get to the answer. Love this example because you can clearly see days to the minus 1 and days cancel. Anything that is in this exponential does have to cancel all of its units. We end up with units of micrograms. And the number is 0.726 micrograms. Which, if you think about it, so 8 days it should be cut in half to about 4.1 grams, 16 days, 2.1, 32 days, 24 days, sorry, 3 half grams. Anyway, so the answer makes approximate sense. Any questions about this? I know we all love kinetics, so this is like so refreshing. Now let's talk about radiocarbon dating. If I started my own version of OkCupid, it would be radiocarbondating.com. It would be for scientists, but that's a different entrepreneurial idea. It is based on the fact that there is a nearly constant amount of carbon-14 in our atmosphere. It comes from cosmic rays from outer space containing neutrons that react with nitrogen-14 in the atmosphere. The reaction that I'm just about to show you is different from every other nuclear reaction I've shown you today. In every reaction I've shown you so far, well, I guess there was 1 or 2 exceptions. You started with one particle, and it radioactively decayed into more than one, with the obvious exception of the positron-electron annihilation and the one electron. But this is a new type of reaction. It's called nuclear transmutation. We'll see more of it, but for now, nuclear transmutation contains 2 reactants, and when those 2 reactants collide, there is a nuclear reaction. Things about the nuclei change. In this particular case, we're going to have carbon-14 reacting with a neutron from the atmosphere. Our neutron still has the same nuclear symbol as before. And in this particular case, I've told you that it's going to form carbon-14. And it is true that for nuclear reactions, I have to tell you everything about them, and you can fill in the last part that I don't tell you based on the rules for balancing nuclear reactions. In this particular case, we know that it has to be 1 down there, it has to be 1 on top. Anybody remember what particle that is? It is a proton. Thank you. So, and in this particular problem, that's the one we filled in because we had enough information for all the other ones. Although it's not how I would state it on the exam, it does have enough information. The carbon, so this is happening all the time. There's plenty of nitrogen-14 in the atmosphere, and it is being transmuted into carbon-14. The carbon-14 is incorporated in compounds such as carbon dioxide. This gets photosynthesized, probably not a real word, but I'm going to pretend, or a real verb, into plant material, then eaten by animals. The carbon-14 is constantly decaying by beta emission, and the half-life of carbon-14 is 5,715 years. So, carbon-14 made into nitrogen-14 made into carbon-14, it becomes carbon dioxide. Carbon dioxide by plants. All right, this is my version of photosynthesis, where I will, in particular, make sure that this, at least some of it is carbon-14, not all of it, but some of it. But we'll pretend that all of it is. That carbon dioxide with carbon-14 gets turned into some glucose, whether you're a plant and you this happens, you photosynthesize it, and then it's inside your materials, inside your carbon, right? What happens to the glucose? That carbon in that glucose gets turned into everything else in the plants. Again, not my area. But and whether you're a plant or whether you're an animal that eats plants or whether you're an animal that eats animals that eats plants, you get carbon-14. And so, at this point I want to say that radiocarbon dating is for plants and animals, or things made from plants or animals. All right. Question? And even vegans. Did I eat plants? All right. An equilibrium is established as long as the plant or animal is alive. The carbon-14 is being replaced at the same rate it is going away. After death, carbon-14 levels drop. Why do they drop? Because you're not eating anything anymore. You're not photosynthesizing anything. Yes, Travis?
For the reaction to the nuclear transition creates the proton, would we assume that it's an aqueous solution that would be treated at a hydrogen ion?
Good question. This proton, how do we treat it? So this is happening in the upper atmosphere, but certainly these reactions can occur in water, and yes, that would be a hydrogen ion. Yeah, nice.
So it would become acidic that reaction.
It would become acidic if the reaction, yes. So, right, so the carbon-14 levels drop. So, as far as determining the age of a plant, if live plant material has carbon-14 at a level that generates 15.3 dpm, 15.3 dPm is 15.3 disintegrations per minute. And it is a rate of radioactive decay. So we can use it in our first order integrated. Per gram of carbon, these measurements, not as simple as we are describing them, but the process does work this well. How old is a piece of parchment paper if the measured activity of carbon-14 is 11.8 disintegrations per minute? So, rate initial or rate at time equals 0. Rate at time t equals 11.8. How old means we're solving for time. And we will plug it into our natural logarithm version of our integrated rate law. Where on the previous slide, we were told that the half-life of carbon-14 is 5,715 years. And K in this case is 1.21 times 10 to the minus 4th years to the minus 1. And we can now plug all our numbers in. Where I've put my rate constant K. Here comes this question, Jim. Oh, where did I get T half? From the previous slide.
Thank you.
Yep. And if this were a problem on your exam, the half-life would be built into the problem. Rearranging and solving for the math, you get 2.1 times 10 to the 3rd years old. Or years since the plant died. And even though I typically go to 3 sig figs for everything, I would suggest that in this method, you're lucky if you can get 2 sig figs, and so that's what I went with here. These measurements in practice are much harder than the problems that we used to create them, and so whenever you hear about something that was radiocarbon dated, think about how accurately they know it. That is a real challenge. Okay. Okay, so always a good question, always a fair question. If I were to ask you to write this reaction on an exam, what would the problem look like? I will now answer that question. Nitrogen 14, or sorry, we should start this way. Neutrons are colliding with nitrogen 14 to make carbon 14. Write the nuclear reaction. I have to be that clear. Does that help? Yeah, I have to tell you 3 of them. I have to, in particular, tell you that these 2 are colliding, right? Because that's physically, I mean, that's how all reactions happen in the end. But in this case, what typically happens when, like, okay, so that's happening in the upper atmosphere, right? So nitrogen, which is a gas, it's usually in the form of N2, is, then here comes the neutron from the cosmic ray, and that's how it collides. When they do nuclear reactions, say, at the Stanford Linear Accelerator, also called SLAC, and they want to make radioisotopes for that PET, positron emission tomography. They'll take some sort of metal, maybe it's cobalt, and they'll take alpha particles or whatever they're doing, and they'll shoot them into it, and the cobalt will be a solid, so you'll know where it is. But it is like the one, some slightly tricky thing, I think, or I'm sure there's lots of tricky things, but when I talk about these reactions, I will typically say neutrons are collided with. Right? So, because that's usually how it's done.
This is not why you write.
Oh, so then why did I write this? I have 7, so I have to have 6 plus 1. Yeah. I have 15, so I have to have 14 plus 1. So that's just balancing the nuclear reactions. And that's the same thing, meaning if it's a radioactive decay, you have to do that. And then if it's a nuclear transmutation, or every once in a while you'll see 2 things on this side and 3 things on this side, but they'll still follow those same rules. That seems like a perfectly good place to stop for today. We'll finish up nuclear chemistry in our next lecture. And I have to go today, so if you have any questions, I'm happy to answer them by email, but I'm going to try and get out of here today.